All right, guys, so today what we're going to be doing is exploring the graphs of these two types of functions that we've been dealing with over the last couple days. We're going to be talking about exponential functions, and we're going to be talking about logarithmic functions, which we know are just inverses of each other, right? So since we know that they're inverses, we really know that they have very similar properties. The only difference is that one is just the reflection of the other over that line y equals x. One thing that I want to point out before we get started is that these checklist statements are just left over from the last lesson. What they should actually say is that I can graph an exponential function and I can identify the critical values of an exponential function. So I'll just write that here so that you can write it in. All right, so we've got two functions here, and we're going to start off by just graphing both of them. I'm going to graph the f of x function in blue, and I will graph the g of x function in green, and you'll notice immediately that we have two specifically different types of functions here. Our blue function is an exponential function, and our green function is a logarithmic function. So we're going to start off by making a table of values to represent each of these two functions. Now, we could do this all by hand, but we know by now probably that that's not the most efficient way to do things. Probably what we should do would be to use a graphing calculator or Desmos to help us figure out what values should be in these tables and what values are on the graph. So what I'm going to do is I'm going to pull up Desmos right here and walk you through how to basically identify what points we should put on this graph. All right, I started putting the functions into Desmos here, but I do want to show you how to grab the log base function. It's over here in miscellaneous functions. You can select log with a base of a, and that'll allow you to change the base of the function. So I can put log base 2 of x plus 2 minus 3. All right, so here are my functions. This is what they look like, but I want to represent that in my notes. So what I'm going to do is I'm going to take these functions and I'm going to turn them into tables so that I can see the table of values that makes this function. All right, and with these two tables, I want to go back as far as I possibly can. So even if I don't see a value here that's useful to me, like 2 doesn't help me much because the range of my function on the table is only up to 10 and this point won't be on the graph. So maybe I'd rather represent this differently. Maybe I should just put -2 and see what we get. Well, we already have -2. Why don't I do -3? All right, so we have a point -3 also. It's best to try to get 5 points if we can. So what I'm going to do is I'm going to represent that here on the table. Okay, so I filled in my f of x function table with a bunch of points. I've got some points here for my g of x function, but I only see 3 points. And I'd really like to have at least 4, ideally 5. So what I'm going to do is I'm going to replace this -0.2 because this function becomes undefined if I go that far. I'm going to see what happens if I go to -1.5. All right, that would give me -4. That's a good point to use. And then I can just keep moving in this direction. I can go with 3, then 4. Nope, that doesn't give me anything. 5 doesn't really help me. 6 is a point I could use. All right, so these are the points I'll use because I have 1, 2, 3, 4, 5 points that all have whole numbers. So I'll use those for my g of x function. All right, so the reason I did this is just so that you see in a situation on a test where you're expected to graph something, I hope that all you do is just pull up the graph on your graphing calculator, make a table, and show it on the paper, and then plot the points that you see. So that's all we're going to do right now. All right, so let me get rid of that graph. Now let's plot these. So I'm going to plot these points in here. I'll pause it and do it so we don't take up too much time. But you should be able to pause and plot these points all by yourself as well. Okay, so now we've plotted the points. And what I can do, and I've seen the graphs of what these look like, is connect these points. And we know that exponential functions, we've dealt with these for a couple days now, and we've looked at the graphs a little bit. We know that they have a line that eventually becomes something like a boundary for that function that it never ever actually crosses. And we just saw the graph of this function, and we noticed that in this area, as we approach -infinity, x tapers off and gets really, really close to this line here, but will never actually touch it. And we're going to have to make a note of that right now because that's a huge point that we're trying to make today is that that exponential function has this thing that is a line that it will never ever actually touch. Now, logarithmic functions are just inverses of exponential functions, so they also have that line. And you probably noticed that with g of x, it had a very similar thing happening as y approaches negative infinity. So that's to say that as we travel this direction, as y approaches negative infinity, it gets really, really close to this line, but never actually touches it. So we've got another one of those here for our g of x function. And part of the reason that we're doing this in two different colors is that you can see that these functions behave very similarly, but they each have this line. This line is a really important line. It's called an asymptote. So what I'm going to do is up here at the top, we're going to define the word asymptote. So what an asymptote is it's a line that a curve is going to approach but will never actually reach. And it doesn't matter what direction we're really talking about either, because a lot of different functions have asymptotes of all different kinds. But these exponential functions will always have an asymptote, one of them. So an exponential is always going to have an asymptote that runs horizontally, and that's because these functions behave in this way. But if we reflect them over that line y equals x, and we use their inverses, those are called logarithmic functions, and they also have asymptotes, but those asymptotes are going to be vertical. And that's the major difference here, and the thing that I really want you to see. For starters, logarithmic functions have vertical asymptotes. Exponential functions have horizontal asymptotes. So the other thing is, where are these asymptotes? Well, this function f of x, as we identified, it is an exponential function, so it has a horizontal asymptote. And we said that g of x is a logarithmic function, so g of x is logarithmic, so it will have a vertical asymptote. Okay, but where are they? And that's something really important too. So let's look at this function, this f of x function. This f of x function's equation is 2 to the x plus 2 power minus 3. And I notice that its horizontal asymptote is at y equals negative 3. And that's a big thing to point out. This is the line y equals negative 3. And you'll notice that it has a negative 3 in one part of its equation as well. So its horizontal asymptote is at y equals negative 3. Now, by that same logic, if we think about our logarithmic function, maybe we would look at it and say, okay, well, it must also have an asymptote at negative 3. But it doesn't, because logarithmic functions are different, right? They are inverses of exponential functions. So it's not the d value, as we've sometimes called this, that controls the asymptote. If we look at this asymptote here, this is not the line x equals negative 3. This is the line x equals negative 2. All right, so how would we be able to find that by looking at our equation? Well, we're not actually going to be looking at our d value. We're going to be looking at our c value. So in this case, it's x equals negative 2. And let's identify what this pattern is here. Because I'm getting a 2 here, but I'm not getting a 2. I'm getting a negative 2 in my equation. So here's another pattern that we need to recognize here. We have two different types of functions. We have exponential, and we have logarithmic. And what I'm going to do right here is I'm just going to write out the general form of each, including all variables that we could change. So, exponential functions. We talked about them numerous times here. We know that they have horizontal asymptotes. And we know that logarithmic functions have vertical asymptotes. But where are they? Well, this exponential function here, with a lot of unknown stuff, this exponential function has a horizontal asymptote that is the line y equals, and we talked about the fact that we know this number because of the vertical shift of that exponential function. So it's actually d that's controlling that vertical shift. Y equals d tells us the asymptote of this function. Logarithmic functions are a little different. We know that it's going to be vertical, so we'll have the line x equals. But if you notice from this pattern earlier, this was the vertical asymptote x equals negative 2. but in our equation we had an x plus 2. Remember that horizontal shifts go the opposite direction of whatever that sign is. So the variable that's controlling the asymptote in a logarithmic function is c, but the line is going to be x equals negative c. So this is how we will determine what the asymptote of these functions is. And we'll talk a little bit more about it when we get into class tomorrow. We'll look at this thing and figure out what the roots are and that sort of thing. But the big thing right now is you should be able to look at an equation and tell me immediately what its asymptotes are. I don't want to make this video too long, but I'll just give two real quick examples here at the end. Let's take these two functions just for example. This is an exponential function right here, h of x. So it's exponential, which means that it has a horizontal asymptote, which means all I have to do is look at d. So the horizontal asymptote is at y equals negative 2. All right, now k of x is a logarithmic function, which means it has a vertical asymptote, which means all I have to do is look at the number that's inside here, the horizontal shift, and make it negative. So the vertical asymptote would be x equals 4. All right, we'll do a lot more of this in class, but that's the general gist. Hopefully you understand the idea behind how to determine the asymptote just by looking at the equation.